In this video, I want to look at constant multiples and antiderivatives. And I want to start by reminding myself about what I know in terms of derivatives in constant multiples. So I want to start by thinking about this basic fact from Calculus 1. If I happen to have the derivative of a constant times a function, I know that I can bring the constant through the derivative operator and say that the derivative of a constant times f of x is going to be a constant times the derivative. In other words, it's going to be c times f prime. So if we let little f of x have antiderivative capital F of x plus whatever constant that we want to add, that says that capital F prime is equal to little f of x, then what I know is that the derivative of c times capital F of x is c times f prime, but capital F prime is just little f of x. So now I can rewrite this derivative fact right here as an integral fact. If I want to find an antiderivative for c times little f of x, that's simply going to be c times capital F of x plus whatever constant I want to add. I'm going to call it a c1. But I can also rewrite this thing completely in terms of integral notation. In other words, I can say that the antiderivative of c times little f of x is equal to c times the antiderivative for little f of x dx. And this embeds this c1 constant as part of this notation. What I want to do now is I actually want to basically think in terms of what this is saying. So in English, this says that if I have an integral sign that has a multiplicative constant inside of it, the multiplicative constant can be pulled through the integral sign. So we can pull multiplicative constants through the integral sign. Well, let's actually look at a couple of examples about how this is going to work. So let's look at example 1. This is going to be a very easy example. Suppose we just have the integral of something like 5 times the secant squared of x dx. I can pull this 5 outside and rewrite this as 5 times the integral of secant squared dx. And this is something that I can recognize. The antiderivative of secant squared is known to be tangent because the derivative of tangent is secant squared. Let's do our basic check. If we differentiate our answer, we're going to have the derivative of 5 times the tangent of x plus the derivative of a constant, which is a big fat 0. And this 5, of course, comes through the derivative operator. And the derivative of the tangent is known to be secant squared. So our answer works because when I differentiate our answer, I get the integrand. Well, let's look at another basic example. This one we're going to combine the constant multiple rule with the sum and difference rules. So let's try and find the antiderivative for 5x squared plus 3x minus 9. Well, what I want to do is I want to kind of break this up into 3 little integrals. This can be broken up as 5x squared plus the integral, I should say dx there, so let me get my notation correct, plus the integral of 3x dx minus the integral of 9 dx. Now, this is going to be 5 times the integral of x squared dx. And the next one would be 3 times the integral of x dx. And this one would be minus 9 times the integral of just dx. And I'm going to want to talk about that one in a little bit of detail in just a minute. These other two are easy to do because they follow one of our basic rules that we've already established. This one's going to be 5 times x cubed over 3. And the next one is going to be 3 times x squared over 2. And then finally, I've got 9 times something. And I kind of want to talk about this over here in just a little bit of detail. If I'm looking at the integral of just a dx, that is technically the integral of 1 times dx. And I know that the derivative of a single x is equal to 1. So the antiderivative of 1 is just going to be x. So this particular integral down here is going to be 9x, and then I have any constant that I want to add. So the antiderivative of 5x squared plus 3x minus 9 is going to be 5x cubed over 3 plus 3x squared over 2 minus 9x plus whatever constant you want to add. Again, let's check by differentiating our answer. If I look at d dx of 5x cubed over 3 plus 3x squared over 2 minus 9x plus a constant, that derivative is going to be, well, let's see, the derivative of this first part is going to be 3 times 5x squared over 3, and the derivative of this part is going to be 2 times 3 halves x, and the derivative of this part is going to be a minus 9 times a 1, and the derivative of that constant is going to be a big fat 0. And when I clean up my algebra, I'm going to have those 3's cancel, and I'm going to have a 5x squared. Those 2's cancel, and I'm going to have plus 3x, and I'm going to have a minus 9. And this is indeed the integrand that I started with. It's the stuff that is inside my integral, and so I know that I did my work correct. Let's look at one more example. Oops. So as a third example, let's look at finding an antiderivative of, say, the cosine of x plus 3 dx. 3x dx. Let's do it that. So this would be the integral of cosine of x plus the integral of 3x dx. And so this is going to wind up going back to, let's see, cosine is the derivative of sine, and then this would be 3 times the integral of x dx. So we're going to have sine of x plus 3x squared over 2 plus a constant. And for our check, if I differentiate sine x plus 3x squared over 2, we will get cosine of x plus 3x. And so our check works. So this is the check.